Hi everyone, I'm Giovanni Barbarani, a PhD student at Politecnico di Torino, and I'm going to present scale-free image keypoints using differentiable persistent homology. If you're interested in learning more, 2 papers have already been published on our project. To begin with, our field of application is image matching, which consists of understanding the relationship between two different viewpoints of the same subject. In particular, we are interested in key point detection, the task of identifying pixel location that remains robust under perspective changes. For example, the intersection between two lines or corner points. The task is commonly addressed using deep learning and convolutional neural networks, which model key points as the local maxima of a scalar feature map at inference time, while during the training phase requires relaxing the notion of local maxima in a suitable way for gradient-based optimization, usually by taking the maximum in each fixed size image patch. We point out that using fixed size image patches during training introduces a bias in the frequency of key points, leading to scale inconsistencies. To model local maxima without introducing scale parameter, we adopt tools from Morse theory. This framework establishes a connection between the critical points of a function and the changes in the topology of its sublevel set, when these are filtered from bottom to top. In the example, we observe that starting from an empty set, a connected component appears at the global minimum. Then new holes emerge at saddle points, and finally these holes are in correspondence, are filled in correspondence with local maxima. Thus, we can model a local maximum through the lifespan of its associated topological feature. This quantity, known as persistence, is defined as the difference between the function value at the maximum and the value at the saddle point that created the corresponding hole. In the discrete setting, we could represent a digital image as a topological space via cubical complexes. In this structure, vertices correspond to pixels, and edges and faces connect adjacent pixels. Moreover, a scalar function defined on pixels can easily be extended to edges and faces by taking the maximum value across adjacent pixels. Thanks to the topological formulation of critical points, the notion can be directly extended to discrete structures. We say that a pixel is critical if its value corresponds to a topological change in the sublevel set filtration. In the example shown in the slides, at time equal t2, we find a critical pixel corresponding to a saddle point, since it creates a new hole. And at time equal t4, we find a critical pixel corresponding to a maximum, because it fills the hole. Within this framework, our contribution is a new detector loss that is suitable for gradient-based optimization and does not require any scale parameter. In practice, our objective function aims at maximizing the total persistence, which lead the model to produce as many local maxima as possible. But at the same time, we introduced a penalty term that enforces the value of critical pixel to be reproducible across different images of the same scene. This image shows a key point detected by our model, namely MorseDet, compared with the previous method based on fixed size patch loss. Thanks to our topological loss, MorseDet is capable of detecting key points at multiple scales, adapting to the image content. Thank you for your attention, and please feel free to reach out if you have any question.